Hello all and welcome back. Okay, so I hope you enjoyed the biology section of this past paper. We are now moving on. We're going to smash out the chemistry section. Let's keep going and keep working hard. You've done well so far, so let's see how we get on. Diamond is used in jewellery. Explain why. Right, straightforward question, yeah? So you're thinking, oh, there must be a trick question. No, honestly, it's that easy. There's loads of different answers. You could have lustrous, you could have colourless, clear, transparent, you could have shiny, sparkly, okay? Loads and loads of different things. You're not allowed to say about the fact that it's really hard. You can't say about the cost, because obviously those aren't reasons why we would use it in jewellery. But you got all those different answers that you could put it in really, really easy. I'm just going to put shiny, okay? Because that's the easiest one, I think. Shiny. That's a mark. Literally just putting shiny by there, okay? Let's move it on. Graphite is another allotrope of carbon. Graphite is used in pencil leads. Look at the structure of graphite. Explain using ideas about structure and bonding why graphite is used in pencil leads. So there's a couple of things that we have to be really, really specific with here, okay? So ideas about structure and bonding and why is graphite used in pencil leads. Okay, so we've got a link, structure and bonding to the fact that it's used in pencil leads. And again, it's a really straightforward question. So you should remember that these forces in between the layers, these dotted lines, they are weak. So that's your first mark, is weak, intermolecular, but you could just say weak forces between layers. That's one mark, yeah? One mark, there it is, boom. Okay, second mark is just explaining the fact that those layers can slide over each other, okay? So fit it in down here. So the layers slide over each other. That's it, done. Happy days, yeah? 3 marks in the bag. We should be happy with that. And those are 3 really, really easy marks. On to the next page. So, here we go, still on the topic of diamond and allotropes of carbon, but it's kind of given us a little twist here. So both diamond and graphite have giant molecular structures. Silicon dioxide also has a giant molecular structure. Look at the structure of silicon dioxide. Explain using ideas about structure and bonding again. Yeah, so we're talking about structure and bonding again. Why silicon dioxide has a high melting point. So you're thinking, why does it have a high melting point? And so the simple answer is two marks again. So we need 2 marking points, okay? First off, we've got strong covalent bonds. Should be remembering that silicon and oxygen, we're going to have these little bonds here. These are all going to be covalent bonds, really strong covalent bonds. If they're strong bonds, that means for our second marking point, there's lots of energy needed. Don't be suckered into saying there's lots of heat that's needed, okay? It's energy that we want. Energy breaks bonds. Energy is what we want, okay? So strong covalent bonds, and so lots of energy needed, another 2 marks in the bag, yeah? Let's move it on. Okay, here we go. Nice, tricky maths question coming up for you guys. I know you love them. So we've got a simple diagram of our of measuring energy transferred by different liquid fuels. We've got a results table, but oh no, there's some gaps in our results table, so you know they're going to try and make you find out what those gaps are. So if we read through the actual question, so look at the results for propanol. Tim and Liz calculate that propanol transfers 7,560 joules of energy to the water. Use the equation, energy equals mass times specific heat capacity times temperature change, to calculate the final temperature of water in the experiment with propanol. The specific heat capacity of water is 4.2 joules per gram per degree Celsius, okay? So here it is. So first and foremost, easiest way to do this is we need to look at these, energy, mass, SHC, and temperature change, and see which ones we know and which ones we don't know, okay? So if we think about energy we know we've got 7,560 joules, okay? It says in the question, just up here. Then we think about mass. So mass, we know if we have a look up a little bit higher, oops, sorry, not higher. Where does it tell us? There it is. Sorry, in the diagram, it tells us we've got 100 grams of water, so that's our mass. So we know we've got 100 grams. Specific heat capacity, it tells us in the question. So then we've got SHC gives us 4.2, and then temperature change is what it's actually asking us to find out. Okay, so temperature change is our question mark. So if we plug that all into the equation, we know we're going to have 7560 equals 100 times 4.2 times question mark. Okay, easiest step first, 100 times 4.2. So we've got 420 times question mark. Okay, and that still equals 7560. Okay, so to find question mark, we need to move 420 from here over to here. How do we do that? We divide by 420 on both sides. So we go 7560 divided by 420 equals question mark, which when you plug into your calculator, if you just give me a second, so we'll go 7560 divided by 420 gives us 18. Okay, 18 degrees Celsius, 2 marks in the bag. Now this, like I said, is a tricky one, but if you've got a bit of confidence in maths, have a go at it. Yeah, it's a very straightforward question. If you just go step by step, what do I know? How do I find out? And just work it through. Okay, it's just a bit of thinking that you need to do for this one. On to the next page. Okay, here it is. Look at the equation for burning ethanol. So it's kind of it's moving on a little bit from our last one. During the reaction, bonds are broken and new bonds are made. Complete the sentence. Okay, guys, if you don't know it, I know like you should know it, and that's great. But if you don't know it, just have a guess. You don't get taken marks off if you don't if you get it wrong. So just have a go. But you should remember that during the reaction, bonds are broken and new bonds made. Complete the sentence. When bonds are broken, energy is, and you should be thinking, yes, I know it is absorbed. They absorb energy when the bonds are broken. And then making new bonds is, so slightly different, but along the same lines, is exothermic, because that energy is being released. Okay, bonds making, energy is released. Bonds breaking, energy is absorbed. Okay, and that is that page. That's it. 2 marks. Boom. Done. Quick. So on we go. Here we go. Questions about rates of reaction. You should be going, yes, there's rates of reaction in this, because rates of reaction are so easy. It's a big part of the chemistry, but it should be a part that you're really confident with, or at least I'd hope you're really confident with. Okay, so here we go. Question 6a. The indigestion tablet contains calcium carbonate, CaCO3. Calcium carbonate reacts with hydrochloric acid, HCl. Calcium chloride, CaCl. Water and carbon dioxide are made. Write a balanced symbol equation. You should be going, yes, easy marks. Yes, here we go. So what you've got to think about, they've given you all the symbols in there other than the one for water and carbon dioxide. Okay, so what you go, so in blue, I'm going to highlight all the stuff that we end up with. Yeah, so you read through it again, indigestion tablets, blah, 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 and you go, all right, calcium chloride, water and carbon dioxide are made. Those are the things that are going to go after our arrow. They are being made. What have we made them from? Then we can see, look, calcium carbonate and hydrochloric acid. Those are the things we started with. So that's just literally the first mark is just for rearranging all that. So if we go CaCO3 plus HCl, so that's what we started with, and then we go, what do we finish with? Well, CaCl2, I am going to struggle a little bit with the room here, H2O, because it's water, and CO2. Okay, brilliant. That's 1 mark. Yeah, easy 1 mark. Now the second mark is where it gets a little bit trickier, but it's still pretty easy, okay? This is a very simple equation to balance. All you have to do is have a look at what have you got on both sides of the arrow. So you can see, let's start with calcium. We've got 1 calcium on either side of the arrow. There it is, 1 and 1. So that's fine. Leave that alone. Look at carbon. We've got 1 carbon on each side of the arrow. Happy days. Move on. Look at oxygen. We've got 3 oxygens there. We've got 1 there and 2 there. So there's 3 over on that side. Bingo. Done. Not a problem. Here where this is where we fall down a bit. Hydrogen. We've got 1 over here. We've got 2 over there. Oh dear. We're missing 1 on the left. Chlorine. We've got 1 over there. We've got 2 over there. Oh dear. We're missing 1 on the left. But you should be going, wait a minute. That means it's really easy to balance. That means that if I just put a big 2 in front of hydrochloric acid, it means that we've done it. There's our 2 marks, okay? That's a balanced symbol equation. Symbol equation part is the easy part. The balancing is a little bit trickier. But if you just think through it, it makes it so much easier. And so the final question on this paper for the 6 marker, obviously, which I'll do in a separate video, like I said, is the indigestion tablet is the limiting reactant. What is meant by the limiting reactant? So you should, again, just be thinking through, what's the limiting reactant? I remember this, rates of reaction, limiting reactant. What is it? Here it goes. So a limiting reactant, you've got loads of options to write in here, but the reactant that's not in excess, the reactant that is used up. Would get you the mark. How easy is that? Used up, sorry, not just used. Used up. There's your mark. So the next section is the 6 marker. Again, we'll skip past that for now. I'll do either a separate video for it, or we'll talk about it in class. Okay. So on to question 7 for us. Questions about pharmaceutical drugs. All right. Aspirin is a painkiller used to treat headaches and reduce fevers. The pharmaceutical company makes aspirin using the following reaction. Okay, so it's supposed to be a complicated reaction. It's supposed to look really, really scary. Don't worry about it, all right? They're sneaky. They try to put stuff in like this that's going to freak you out and put you off your game, all right? Ignore them. Let's get on with it. So, ethanoic acid is a waste product. Look at the table of relative formula masses. Calculate the atom economy for the manufacture of aspirin. So you should remember that the atom economy is going to be the MR of desired products divided by the sum of the MR of all products times by 100. All right. So here we go. So the MR of our desired product, you can see that obviously aspirin is our MR, and we have a little look in our table. There's aspirin. So we know that the MR of our desired products is 180. Now we need to work out the MR of our total products made. So we know that ethanoic acid is another product that we've made. So we look C2H4O2, there it is, 60. So we know that 180 is going to be divided by the aspirin and the ethanoic acid, because that's everything that we've made, and it's going to be times by 100. Now what's useful in some of these questions is just to press equals on your calculator almost as often as you possibly can, because all you have to do is do, so 180 plus 60 gives us 240, so we do 180 divided by 240 and then press the equal sign. It gives us 0.75. Then we do 0.75 times by 100, it gives us 75, okay? So you should be thinking 75 what? Well, of course, that is 75%, all right? You do actually get the mark without the percentage sign, but you do have to be a little bit careful sometimes to make sure that it's in there. Right, the pharmaceutical company wants as high an atom economy as possible. Explain why this makes the process greener. Okay, so 1 mark question, shouldn't be thinking too hard about this. Loads of marks available, so you could have any one from to make the process more sustainable, to make the process more efficient, to reduce the processing or unwanted products, to conserve raw materials. I mean, the easiest one for me is there's less waste product. There you go. Easy 1 mark, done. Happy days, let's move on. So the pharmaceutical company makes several batches of aspirin. They test the melting point of each batch to check for its purity. The melting point of pure aspirin is 135 degrees. Look at their results. Which batch contains the purest sample of aspirin? Okay, so again, not a trick question, but they just want you to start thinking about which one's closest to the 135 that we want. And as you can see, the closest one is C. Okay, you could argue that there's some pure stuff in B, but because it's going from 131 up to 134, it means we've got a bit of a mixture. We've got maybe have some pure stuff, and then some not so pure stuff. 128 is too far away, and 138 is too high. Okay, so 134 is the closest, and that's all you got to say to get your marks. The fact that C is just below, so it's just below the real melting point of 135. And that'd be your 2 marks. So you've chosen C, and you've given me a reason why, and there's 2 marks. You could also have that C is not a range of numbers, like I said for B, because 131 to 134. And you could also say that the more impure a substance, the lower its melting point. So you've got loads of options there, but again, it's a really easy question to do very, very well on. Okay, nearly there, guys. Stay with me. So let's move on to the last page that we're going to go through. So aluminium sulfate, A2SO4 is used to help relieve the pain caused by bites and stings. Look at the equation. It shows how aluminium sulfate can be made. And again, they've put in a big, scary equation to try and intimidate you, but you're not going to be intimidated. Show that the relative formula mass of aluminium sulfate is 342. So they've told you the answer, but you need to show how this works, okay? So that you need to show, they've told you all the different molecular weights, and you need to work it out. So step 1 of this, although it's only worth 1 mark, it is worth doing it right. So we work out how many of each element we have in that aluminium sulfate. So if we highlight the aluminium sulfate, there it is, Al2SO4. So we work out, obviously, aluminium, we're going to have 2. Okay, we've got sulfur, we've got 3 of, because you can see that there's that little 3 down there that's telling us that we've got 3 of it, so we'll just put a 3 by there. And then finally, a little bit tricky, but you've got to think about it, we've got oxygen. Okay, now oxygen, inside the bracket's got 4, so it's got an O4 group, but outside the bracket it's telling us that there's 3 lots of that 4 group. So we go through our 4 times table, 4, 8, 12, we know that there's 12 oxygens in there. Okay, next up, we look at what each of these weigh. So we've got them, they've told us them, they're just here, aluminium, oxygen, and sulfur. And so we go aluminium, we know we've got 2 of, and we know it weighs 27. So we know 2 times 27, and we'll work that in a minute. Sulfur, know it weighs 32, and we know we've got 3 of them. And oxygen, we know it weighs 16, and we know we've got 12 of them. And so then it's literally just a case of working through the maths. So we do 2 times 27, which gives us 54. We do 3 times 32, which gives us 96. And we do 12 times 16, which gives us 192. And then you just add them all up, which will give us the total that they've already told us, okay? Which will give us 3, 4, 2, and you've proven it, okay? Although it seems like a lot of work for 1 mark, that 1 mark could be the difference between your target grade and falling below your target grade, okay? So let's, we do have to work towards it, and there it is. Last question, guys. You've done so well. Let's finish on a high, yeah? So, look at the table, relative formula masses, yeah, we've got loads of different elements. Use the information in the table and the balance symbol equation to show that the mass is conserved when aluminium sulfate is made. Okay, so you're going to be freaking out again. You're going to be going, what does mass conserved? What does that mean? What does that mean? It's really straightforward, guys. All you got to do is you got to show that everything on this side of the equation is equal to everything on this side of the equation. All right, so it does take a little bit of to and fro, and I'm going to zoom out a little bit so we can just have a little look at that equation at the same time as doing it. So we just need to add up everything that's on that left-hand side. So first off, we know we've got this group, which we can match up by here, okay? So that's 78. But don't be fooled, there is a 2 at the front there, so we know that we need to do about times by 2. There's a 2, sorry. Let's try that again. 2. Then we look at the next one. So we add on to that. We've got our second group, H2SO4. There's our H2SO4 group. But again, there's a 3 at the start. So we've got 98 times by 3. Okay. Then at the back end, we can see that obviously Al2SO4 3, we did all that hard work to work that one out. So that's 342 by there and there. And then finally, we've got H2O. We've got H2O, but we've got 6 of them. So H2O is 18, but obviously we times by 6 to make that up a little bit. Okay, and we need to add those two together. So back to our calculators. Here we go. We go 78 times by 2, which gives us 156. I'm going to run out of room a little bit here, but it's fine, 156. 98 times by 3, which gives us 294. Then we add those two together. 156 add 294 gives us 450 in total. Okay, so 450 on the left. We are expecting 450 on the right. So if we do 18 times by 6 really quickly, that's 108. I know I've gone off the page, but that's fine. We're going to add it to the 342 that we've already got. So 342 add 108 gives us 450. Look at that. You have proven that no mass has been lost because there's the same on the left as there is on the right. And that is that, guys. That's our chemistry one done, smashed out. So I hope you found that really useful. I hope you're going to be using it. You're going to be looking at this one as well as the biology one, as well as the physics one. And like I said, it's a game changer. It's going to make it better. It's going to make your results go up. Only one direction, yeah? So thanks for listening, guys. Stay classy.